Hi everyone, welcome back. In this video, we're going to talk about the electromagnetic waves. Like we did a video on that where we derived the wave equation and where we derived this equation del square E equals 1 over c square dou square E by dou t square. This is the electromagnetic wave equation in terms of electric field, and we also derived the wave equation in terms of magnetic field. We derived it from the Maxwell's equations. Okay, if you haven't seen that video, if you feel like that's necessary, just go and watch that video as well. Today we're going to see the solution of these wave equations, and we'll try to learn about many things in this video. Okay, I also discussed actually the wave equation for a structured string. Okay, I also discussed the wave equation for a structured string, because knowing that thing makes understanding very much clear, and we make some comparisons as well. Because that's actually elementary physics, we derived actually, we didn't derive actually, we know this thing, dx square equals 1 over v square dou square y. Let me write it y. I'll erase the f. Okay, dou square y by dou t square. Let me erase the f. So this is y. Okay, so this is the wave equation for a structured string, and this v is the speed of the wave, and where y is the displacement of the particle. I discussed all these things in the video. This is the displacement of particle of string. Okay, particle of string, and this v is the speed of wave. V is the speed of wave. Okay, now what we did in the last video was these two things. Now today we'll do the solutions of these things. The solution of this equation, wave equation for a structured string, is y equals a naught sine of omega t minus kx plus phi. Okay, this we know from the very elementary physics, where a naught is the amplitude of the particle. This is the amplitude of the particle that is actually oscillating. Okay, this is the wave. Let's say it's going up and down, so this is the amplitude, a naught. Okay, omega t is the angular frequency, k is the wave vector, and phi is the initial phase. Okay, I don't need to go into details of this solution, but we know, we have learned all these things in the 11th and 12th physics. So what I'll discuss here, I'll discuss some important points. Okay, where a naught is amplitude. This is the first thing you must know. And this wave number, let me tell you first the angular frequency. Angular frequency, omega, is 2 pi by time period, or 2 pi f. Is simply, this is 2 pi is constant, f is the frequency, this is the linear frequency, and this is the angular frequency, and this is the time period. And we can write it in terms of a speed of light as well. It's like 2 pi c by lambda. So it should be actually v by lambda. It's actually, it should be v here, because 2 pi v by lambda, because v is the speed of the wave in a string. Is that okay? Second thing we must know about this thing is wave number k, which is given by actually 2 pi by lambda, where lambda is the wavelength. Okay, or we can write it as a vector as well, because this is very important. This is associated with direction. Actually, this is associated with direction of propagation, in which direction the wave is propagating. Okay, this is very important with that, because in the next videos we'll understand if like we can represent the direction of propagation as a k cap. So this is important, very important. Or like we can write it as a k vector directly. So this is actually a vector quantity. It would be very important. And direction of propagation here will be decided by, so direction of propagation is decided by phase. Phase is decided by, this is phase. Okay, this will decide the direction of propagation. It is important actually, this kx minus omega t. If sine of kx and omega t are opposite, then wave is traveling along positive x direction. So if they are opposite, like kx is positive, this is negative, or we can write this as y equals a naught sine of uh, it's like minus kx plus omega t. Again, it's negative, one is positive, one is negative, so it's again traveling along positive x direction. If both are of same sign, let's assume a naught sine of kx plus omega t, so it means the wave is moving along the negative x direction. Or like a naught sine of minus kx minus omega t, it's still moving along the negative x direction. So the in which direction the wave is traveling, so it is decided by this phase factor, which is very important, omega t minus kx, or you can write kx minus omega t, you can write kx plus omega t, you can write minus kx minus omega t. So that the sign of these two will decide the direction of the propagation. Okay, that is very important point. Y is displacement, this is along the y-axis, y is displacement is going up and down, and wave is traveling along this x direction. Okay, I hope you understand. The displacement of the string, or the displacement of particle of the string is it's doing SHM. That means it is going up and down, while the wave is traveling towards x-axis, or the wave might be traveling towards the negative x-axis. So it's decided by actually this factor. If the solution is like the f equals a naught sine of ky minus omega t. So like this is the let's say here is, let me write it z. So displacement of the particle, the string, this is the string, the particles are going up and down, that means that is z-axis, and wave is traveling, that will be decided by the multiplication coefficient of k, that is y, this is the y-axis, so wave is traveling along the y-axis because the sign is opposite. If the sign would have been like this, negative and negative, then the wave was traveling in this direction. I hope you understand. So from the string, like a stretched string, we understand certain things. Y is the displacement of the particle of the string, and the coefficient of k, the coefficient of k will decide the direction of propagation of wave, and this way is the speed of wave. And how do we calculate speed from the general solution? This is the solution. Okay, and how do we calculate the speed? Speed of wave equals, that is given by the coefficient of t divided by coefficient of x. Okay, so what is the coefficient of t here? Is it's omega, and coefficient of x is k. Okay, I'm saying the magnitude wise. The direction will tell us the in which direction the wave is traveling. Omega is 2 pi into frequency divided by, this is a 2 pi by lambda. Okay, let me write it 2 pi by time period. So 2 pi will go, lambda will go up divided by time, you understand? So it will give us a meter per second. So this is the speed of the wave. If you're not satisfied with this thing, then you can do one thing, that would be a homework. You can put this thing in this solution. I mean like this, you can put this solution in the wave equation. Then what you will get, if when you will solve it, you get this equation, omega square equals v square k square. if you try this thing by putting here in this equation, by putting the y here and here, then comparing, then you will get this thing. So v square would be given by the k omega square by k square. So v, which implies v, is given by omega by k. Okay, so we, in general, actually we write it coefficient of t divided by coefficient of x. So these are very important pointers that you need to remember here in the string. Okay, in the string. One more thing that you need to remember is speed. Here v is given by actually frequency into wavelength. Okay, this is also very important because we'll also use it. Here we can do one thing. Here we can write it c by lambda or v by lambda because we're using this equation here. I hope you understand all these things. Now let's move to our main topic, which is actually the electromagnetic wave. Okay, now see, now we'll move to our main topic of this video, which is the wave equations are del square electric field. In terms of electric field, I'm writing 1 over c square dou square psi by dou t square, and in terms of magnetic field, dou square b equals 1 over c square dou square, what I wrote here is electric field, magnetic field by dou t square. Okay, del square b and here. Okay, they're correct now. Now see, now the solution is given by exactly the same way. Here it was y in the stretched string equation. Here it is electric field. So electric field is actually given by E naught cos of, or you can write in terms of sine, kz minus omega t plus initial phase x cap. Okay, or in some books, I'll explain every point. In some books you can see this x cap with this thing. So electric field is equal to E naught x cap cos of kz minus omega t plus delta. Exactly the same way. See, the coefficient of k, which is z, so which means wave is propagating along z axis. Okay, now this sine of kz and omega t will decide whether it is plus z or minus z. You understand? Exactly the same way. This is the amplitude. E naught is the amplitude. Maximum E naught is amplitude. And the electric field, this electric field is given by this direction, not by this, not by z. The coefficient of k will tell in which the direction wave is propagating. Electric field is varying. Since it was in this solution, it was saying that the amplitude or the wave, actually the particles are moving along the y-axis. So the particles are doing the SHM along the y-axis. But here, in case of the electromagnetic waves, we don't have particles, but rather we have electric field. So this electric field is actually varying along the x cap, along the x direction. Or we can write it in this way. See, in some books you can write it like this: electric field zt equals E naught cos of kz minus omega t plus delta x cap. Or you can see zt equals E naught sine of kz minus omega t plus delta y cap. So you can see wave is traveling along z because the signs are opposite, and the electric field is varying along y. Here along x, wave is traveling along, which is given by the coefficient of k, and here the direction will be always given here. We say it is actually the direction of polarization. Direction of polarization. It is very important point. Very important point. If we treat this as a solution, so x cap is the direction of polarization. And direction of polarization is always decided by the electric field direction. This point is also important, very important. Direction of polarization Direction of polarization means in which the direction electric field is varying. Simply, direction of polarization is decided by electric field direction. Electric field direction. We know from the very beginning, from our higher high school physics, that electric field and magnetic field are perpendicular to each other and are perpendicular direction of the propagation. So if here we decided the electric field is along the x cap and propagation is along the z cap, so then there remains only one axis, which is y axis. That would be the direction of magnetic field. So b zt, it is again wave is traveling along z, and it would be b naught, and which direction would be there? Y direction. Cos of kz minus omega t plus pi. So again, wave is traveling along z because coefficient of k is z. Magnetic field is varying along y. We don't say the polarization is along the y axis. We don't say. If we say that in this equation, what is the direction of polarization? Direction of polarization. If somebody asks you what is the direction of polarization, don't say it is y cap, but rather it is x cap, because direction of polarization and is solely decided by the electric field direction, the axis in which the electric field is varying or oscillating. We know electric field and magnetic field does oscillate. I hope you understand this very important point. Okay, I hope you understand it. Again, I'm saying the direction of the polarization is decided by the electric field direction, not by the magnetic field. Even if they give you this, let's assume somebody asks you a question and he gives like this thing, like x t equals b naught x. Now here it wouldn't be b naught y cos of kx minus omega t plus phi. So this means wave is traveling along x, b naught is varying along y. What is the direction of polarization? Direction of polarization is z cap, because if b is along y, propagation is along x. So it's like this is the propagation x. Let's say this one is the z, and it is a magnetic field. Electric field would be along x direction varying. So this is the electric field along. This is the x-axis, so there would be z. This would be z-axis. So let's say this is the y-axis. Okay, I'm saying I did some writing mistake. Let me tell you again from the equation. So this equation, this is the wave is traveling along x. Let's say this is the x-axis and wave is traveling in this direction. Magnetic field is along y. Let's say this is the y direction. So magnetic field is in this direction. So electric field would surely vary along this z direction. So direction of polarization is along the z, because the polarization is solely decided by the electric field. So electric field is the primary indicator of polarization. There are certain points you need to remember in this case. So let me tell you certain things. Very important point is first, okay, if electric field is parallel to x-axis, x cap direction, so we say wave is polarized along x direction. First. Second, direction of b is always perpendicular to both E and wave propagation, which is k, okay, k cap, or like or the coefficient of k, which is actually z. I'm taking this, okay, I'm taking this as the solution. So electric field is along the x direction and wave is traveling along the z direction. So you can see from the solution that the coefficient of k will decide the direction. So actually it is the k which decides the direction. So even we can say k cap is the direction of propagation, because we know the, like, whatever the factor is associated with the k will decide that thing. Okay. Okay, third point is, at any fixed location, at any fixed location along z. Okay, if this is the propagation, z is the direction of propagation. If you stand at point, if you stand at some point, okay, the fields, the fields vary sinusoidally in time. This point is very important. If e goes up, if e goes up and down along x direction, then b goes side to side along y direction. I hope you understand, because wave is traveling along z direction. Electric field is going up and down along x. It is going up and down along x. Then magnetic field would go side by side along y. Okay, so this is a very important. There are certain important points as well. I'll mention them here. They are in phase. Electric field and the magnetic field are in phase. What that means is that when electric field goes maximum, then magnetic field would go maximum at the same instant of the time. If electric field goes zero at some instant of the time, then magnetic field would also go zero at that instant of the time. So when we, what it means, they are in phase. If E equals zero at some instant of the time, B is also zero at that point of the time. When E is maximum, B is also maximum, but obviously in different direction. And I hope you now understand that, but in different direction. That means they rise and fall together. That is, they rise and fall together. This is very important to what it means in phase. Okay, there is one more question, whether the amplitude of maximum, I mean like the maximum value of electric field and magnetic field are same. No, it doesn't mean that thing. When E becomes zero, B becomes zero. E is maximum, B is maximum at the same instant of the time, but in the different direction. If here is along the x-axis, at some instant of the time, goes it goes maximum, then at the same instant of the time, B goes maximum in the different direction, in this direction. Okay, so that is, they rise and fall together. That's what we would say in phase. But are E naught and B naught same? When E becomes maximum, B becomes maximum, but the value is not same. Value is different. Actually, B naught is equal to E naught by C. This is the very important equation. So if E naught is, let's assume 10 to the power, I'm saying, let's say it's 10 to the power 16. So B naught is like that, 3 into 10 to the power 8. You understand? So the value is different, maximum value is different, but they go maximum at the same instant of the time. I hope you understand. That's why there is a very famous diagram. I don't want to figure that right now to draw. I'm not interested in drawing that figure. So it goes like this. It goes like this. Let me try it. Actually, it's a bit not complicated, but it takes some time. Like that. Okay. Let me redraw it. First one was better. I should have stuck to that thing. Again, it's I don't know what is going on. Okay, now this one is good. Okay, now let me go with, So like it's like, let me close this one, let me try it for you. Okay, let me try it for you. So if this is electric field, then this is magnetic field. It goes here, it goes maximum electric field, magnetic field goes maximum that time. Electric field becomes zero, then magnetic field also becomes zero. Now it increases, that also increases in the opposite direction.